Dr. Pius Augustine and my dear friends, a warm welcome to one and all to the seminar on the topic Radioactive Equilibrium, Measurements of Radioactivity and Radiocarbon Dating. Let me first introduce my team members. They are Hanna Maryam, Devika Mohan, Binta Benny, Sneha Tijo and myself Malavika Chadrakumar. So now let's begin with the seminar so that I invite Hanna Maryam to begin the seminar.
Good day to one and all. Today, I will be presenting on the topic radioactive equilibrium. So, before moving on to my topic, I would like to begin with a question. What do you mean by equilibrium? So, basically, an equilibrium is a condition in which we know that every matter in this universe has to attain an equilibrium state for a proper function. In other words, we can say that when the rate of actions of all phenomena that consider an element is equal, then that element is said to be in equilibrium state. I will explain with an example in this case when we consider the radioactive equilibrium. That is, in this figure we can see an empty bucket and which is open at its top and there is a hole at its bottom. So in first page we can see that water is being collected at the rate of 4 drops per second, and after 1 hour it is filled for 20%, and now in such a manner that the water is being collected at 4 drops per second and it loses water at the rate of 2 drops per second from its bottom. Then again after 2 hours, the bucket is filled with 30% and it gains water at 4 drops per second and loses water at 3 drops per second. And finally, after 100 hours, it reaches a state of equilibrium. That is, the bucket is now filled with 40% in such a manner that the rate of water at which it is being collected is equal to the rate of water at which it leaves from the bucket. So here in this case it is 4 drops per second. So from this we can understand that an equilibrium state can only be obtained after a certain amount of time. Here in this case we can say that 100 hours. So basically for a radioactive element to reach an equilibrium state, it takes about thousands of years to complete or to reach equilibrium state. Now moving on to the definition of equilibrium. So radioactive equilibrium. So we should be familiar with the elements that is involved in this particular element. So parent element. Parent element is actually basically an element which undergoes a certain phenomenon. Here in this case the disintegrating element is referred to as parent element, and the product which is formed after disintegration, commonly known as the offspring of parent element, is known as daughter element. Now equilibrium, it is a state of balance, and as I have explained in the previous concept, it is the radioactive element should be at its equilibrium state so as to attain an equilibrium state. And it is a continuous process until it reaches stability. That means it takes over, it is a continuous process, it is a recurring process, and it takes place after a transition period. That means this transition period can vary from years to years. So, and also radioactive equilibrium, it is based on the law of radioactive disintegration. Now we have seen what is law of radioactive disintegration. That is, the law states that if a radioactive sample contains n nuclei, at a given instant, the ratio of dt, that is minus dn by dt, to the number of nuclei present at that instant is a constant. In much more formulated way, we can formulate this law in the form of dn by dt is equal to minus lambda n, where lambda is the decay constant. In other words, the decay constant signifies the decay probability of a sample. Now, when a particular element or radioactive species has to attain an equilibrium state, the activities of daughters will decrease with the half-life of parent. This is an important point. And for an radioactive element to reach its equilibrium state, the rate of formation should be equal to rate of disintegration, and it is irreversible. Now, coming on to the difference between chemical equilibrium and radioactive equilibrium. So, chemical equilibrium, we have been studying from 8th standard onwards what is meant by chemical equilibrium and the process involved in it. So, basically, chemical equilibrium, so as to attain for a chemical element so as to attain its equilibrium, the forward reaction should be equal to the backward reaction, and in case of radioactivity, the formation rate, that is the rate of formation, should be equal to the rate of decaying process. And in a chemical equilibrium with a certain amount of process involved, we can get back the reactants from its products. That is, it is reversible, and in case of radioactive equilibrium, it is irreversible. Chemical equilibrium, it depends upon temperature and pressure, and radioactive equilibrium, it is independent of temperature and pressure. Chemical equilibrium, it only takes place of a short duration compared to the radioactive equilibrium. In the case of radioactive equilibrium, it takes about years to attain an equilibrium state. Chemical equilibrium is exhibited in non-radio species, and radioactive equilibrium, it is found in radioactive species only. Here is an example given. For a chemical equilibrium, carbon dioxide plus water gives H2CO3, and it is reversible. And radioactive equilibrium, decay of uranium with the mass 238 is an example. Now, coming on to the basic. This is an important derivation. Law of successive disintegration is an important derivation. So, based on explaining the concept of radioactive equilibrium, so this law of successive disintegration actually forms the Bateman equation, and this Bateman equation is required to understand the concepts, that is, certain condition that is involved in the equilibrium state, that is secular condition, no equilibrium condition, and transient condition. So, first we consider an element A, that is a radioactive species, and it undergoes disintegration and it converts into a daughter nuclei B. So here the decay constant can be considered as lambda 1. Similarly, B again undergoes disintegration and it forms C, that is a daughter nuclei, and the rate of decay constant, can be considered as lambda 2. So according to the law of radioactive disintegration, we can say that minus dN1 by dt would be equal to lambda 1 and N1. Here N1 is the rate of concentration after the disintegration process, and we can see that the decay of nuclei A leads to the formation of nuclei B, and that is the rate of decay of nuclei A is equal to the rate of formation of daughter nuclei B. That means the rate of formation of daughter nuclei is equal to lambda 1 N1, and since B also decays into another nuclei, the rate of decay of nuclei B can be considered as lambda 2 N2. So hence the net increase in the rate of B can be considered as dN2 by dt, which is equal to lambda 1 N1 minus lambda 2 N2. So here in this case, we can see that lambda 1 N1 is positive and lambda 2 N2 is negative. Here lambda 2 N2 is negative since it is the decay rate, and in the other case it is the formation rate. Now coming on to the next one. Okay, so based on the law of radioactive disintegration, we get the formula dN by dt equal to minus lambda n. So this formula can be explained in different ways, that is the exponential decay, half-life, mean life, etc. So based on the exponential decay, we can formulate that equation as n1 is equal to n0 e raised to minus lambda 1t, where n0 is the initial concentration. So substituting that equation in the previous equation, we can see that dN2 by dt would be equal to lambda 1 n0 into e raised to minus lambda 1t divided minus lambda 2 n2, and we are taking lambda 2 n2 to the RHS side, then we multiply with e raised to lambda 2t in the next process, and in the next is the product rule. So when we basically when g and y is a function of x, and when we take the derivative of it, we use product rule, that is which is equal to g into the derivative of y plus y into derivative of g. So we are taking the reverse order and we get this equation. Now, then comes the basic integration, and we get the final equation as n2 is n2 into e raised to lambda 2t, which is equal to lambda 1 n0 into e raised to lambda 2 minus lambda 1 t divided by lambda 2 minus lambda 1 plus t, where d is the constant of integration. So our next process will be to find the value of d. For that, we consider the initial condition, that is when t is equal to 0, that is n2 equal to 0. That is in the case where no daughter nuclei is formed, that is before the disintegration process. So from that we get the value d is equal to minus lambda 1 n0 divided by lambda 2 minus lambda 1, and in the next process we can see that we substitute the value of d in the next equation, and we finally get the equation as n2 is equal to lambda 1 n0 into e raised to minus lambda 1 t minus e raised to minus lambda 2 t divided by lambda 2 minus lambda 1, and this is the Bateman equation. It is a very important equation, and this is an important derivation also. So Bateman equation is required to formulate or to explain the concept behind the secular condition and transient condition, which we will be discussing. So secular equilibrium. Secular equilibrium, it actually means extremely long-lived parent nuclei, and extremely long-lived parent nuclei. So in this case, so we can see that the decay constant of daughter nuclei will be very much greater than decay constant of parent nuclei. Here D denotes daughter and P denotes parent. So an equation that connects decay constant and half-life is that lambda is equal to 0.693 by T half. So from that we can get that Tp will be very much greater than Td, and for an secular equilibrium, the activity of parent should be equal to activity of daughter. So in this figure, we can see that there is a graph between activity and time, and the linear curve denotes the activity of daughter, and the constant line, the straight line, denotes the activity of parent. So after a particular amount of time, a stage is reached when the activity of both becomes equal, and in this case, we can say that it is under secular equilibrium. And the equation which is formed is Na by Mb, which is equal to lambda b by lambda a, which is equal to T half of a divided by T half of b. So in the next session, we will be discussing how to get that equation. So activity of daughter. Now, what do you mean by activity? So activity, it is basically represented by the equation lambda n, that is it is the number of disintegration per second of the radioactive sample. So it is denoted by the letter R, and a series of radioactive undergoing disintegration process can be written in the form lambda 1 n1 is equal to lambda 2 n2, which is equal to lambda 3 n3. And the next equation is basically the Bateman equation. And considering the concepts behind the secular equilibrium, we substitute those values. That is, T1 is very much greater than T2, which implies that lambda 2 is very much greater than lambda 1. And for a secular equilibrium, the lambda 1 can be approximately equal to 0, and e raised to minus lambda 1 t will be approximately equal to 1. Substituting those values, we get an equation n2 equal to lambda 1 n0 into 1 minus e raised to minus lambda 2t divided by lambda 2 minus lambda 1. And after a long time, that means for example, for a uranium of mass 238, we can say that it takes about 4.57 billion years to get the next daughter nuclei. So in that case, we can say that e raised to minus lambda 2t will be approximately equal to 0, and n1 will be approximately equal to n0. And here n2, from that we can see that n2 is equal to lambda 1 n1, divided by n lambda 2, and final equation will be as lambda 2 n2, which is equal to lambda 1 n1. From this we can form the previous equation which was seen in the previous slide. Now coming on to the application is very simple. That is, when we know the value of n2 and n1, and also when we know the value of any one of the decay constant, we can find the value of the other decay constant, and it is applicable for the other process, that is vice versa. And when we know the value of n2 and n1 and any one of the half-lives, then we can find the value of the other half-life, and it is vice versa. Now this is an example. Uranium chain decay is an example of a secular equilibrium, and we can see in the figure that uranium 238, that is of mass 238, it takes about 4.5 billion years and it undergoes alpha decay and it obtains thorium. Then it undergoes beta minus decay, and again beta minus decay, and alpha decay, alpha decay, alpha decay, and it is a continuous process and it takes place over a transition period. Now this is another condition based on the law of successive disintegration, that is, when the daughter and parent nuclei of nearly equal half-life. This implies that the lambda 1 will be approximately equal to lambda 2. From this we can conclude their activity ratio as A1 by A2, which is approximately equal to T2 by T1, and the activity ratio is directly proportional with the time. And the example can be is let 200 of 21 hours to 26.4 hours of thallium 200 is an example. Now this is a problem, that is we can based on these type of equation we can see many problems. That is, here we can see a uranium of mass 235 has a half-life of 7.2 into 10 raised to years, and thorium has of mass 231 has a half-life of 24.75 hours. And here the weight of the uranium 235 is given. Our aim is to find the weight of the 231 thorium. So since the half-life is given, since the half-life of uranium is given in the form of years, we have to first convert into hours. Now we consider the secular equilibrium equation, and first of all, and we should be aware that here the weight, the concentration is not given directly. Here the weight of the elements, radioactive species, is given. So in order to find the concentration, we use the equation given weight of element divided by atomic weight of element into Avogadro number. Here Avogadro number is 6.023 into 10 raised to 23 atoms. And substituting those values in the secular equilibrium condition, we get the final answer as a weight of thorium will be 3.856 into 10 raised to minus 12 gram. I hope everyone has understood the concept. Thank you for listening. Now I invite my friend Malavika for the next session.
Thank you, Hanna. That was really an informative session. So, here I am dealing with the topic which is exactly the continuation of what Hanna taught. So, in order to recall it again, first let's see what is radioactive equilibrium. Radioactive equilibrium exists when a radioactive nuclide is decaying at the same rate at which it is being produced. Here, lambda is the decay constant and capital N represents the number of atoms available to decay. If we multiply with each other, we get a radioactive decay rate, that is capital R equal to lambda into N. Since it's a equilibrium, if that is the decay rate of initial parent nuclei and decay rate of unstable daughter nuclei are equal, we get the equation lambda 1 n1 equal to lambda 2 n2. Next slide is also a definition of radioactive equilibrium, and it says that equilibrium condition can be achieved only if both parent and daughter nucleus are radioactive and half-life of daughter is shorter than that of parent. If daughter's half-life exceeds that of parent, equilibrium will never be reached. So, based on this concept, radioactive equilibrium can be divided into three, which are secular equilibrium, transient equilibrium, and no equilibrium. In this slide, we can see all the three conditions at a glance. Let's see how all the three are different from each other. So, the first condition is secular equilibrium, and in secular equilibrium, half-life of parent is much greater than the decay product. That is greater than 100 times than that of decay product. The second condition is transient equilibrium. In transient equilibrium, half-life of parent only greater than the decay product. That is, half-life of parent is greater than 100 times than that of the half-life of daughter product. And the third condition is no equilibrium, and in no equilibrium, half-life of parent less than that of decay product. So this is all the three conditions of radioactive equilibrium. So now let's move on to the example for real life example for radioactive equilibrium, and the first one is nuclear reactor coolant. In nuclear reactor coolant, generation of radioactive sodium-24 happens when it absorbs a neutron from the fission of uranium-235. Another example for radioactive equilibrium is a radionuclide generator. Radionuclide generator is basically a device which provides short-lived daughter radionuclide which is decayed from long-lived parent radionuclide. There is a method of separating the daughter and leaving the parent behind to regenerate more daughter activity. For more details, you can visit the links provided below. So now let's move on to the main topic, that is transient equilibrium. Before that, there is a small picture which shows a radioactive equilibrium. In this picture, we can see a parent nuclei is decaying into a daughter nuclei, and the daughter nuclei, which is radioactive, is undergoing further disintegration, and the daughter nuclei, which is stable, remains constant. So, this is the radioactive equilibrium. Now, the main topic is transient equilibrium. So, transient equilibrium exists when a half-life of the parent nucleus is longer than half-life of daughter nucleus. Here is an example. Here we can see that thorium with a mass of 234 is undergoing disintegration to produce barium 234. Palladium 234, and the series continues. Here we can see that the half-life of parent is 24.1 days and the half-life of daughter is 1.18 minutes. It is clear that the half-life of parent is greater than the half-life of daughter nucleus. So now this is an application of transient equilibrium, that is a molybdenum-99 generator. Molybdenum-99 generator produces technetium-99 for nuclear medicine diagnostic procedures. From this picture, we can see molybdenum-99 is undergoing disintegration to form technetium-99m, which is an isotope of technetium-99m. And a transition happens and finally technetium-99 produces. So here I have provided two links which will give you more details about the molybdenum-99 generator. If you are interested, you can visit these sites. So now let's move on to the derivation of transient equilibrium. Before that, we have to remember a few equations. That is equation of radioactive equilibrium. Lambda 1 n1 equal to lambda 2 n2. And from this equation, here 1 represents A and 2 represents B. So from this equation we get NA divided by NB equal to lambda B divided by lambda A. And also the next equation, T half equal to 0.693 divided by lambda, which is familiar to us, and from this equation we can see that the decay constant is inversely proportional to the half-life. So from all these three equations we get Na divided by Nb equal to lambda b divided by lambda a equal to T half A divided by T half B. So now let's move on to the transient condition. So as per the definition, the half-life of parent is greater than the half-life of daughter. Since decay constant is inversely proportional to half-life, the decay constant of daughter is greater than the parent. So coming to the derivation, here we can it is familiar to us that the activity of daughter nuclei are equal to lambda n. So Na equal to n0 e raised to minus lambda t, which is the basic equation of radioactivity, and Nb equal to n0 lambda a divided by lambda b minus lambda a into e raised to minus lambda at minus e raised to minus lambda bt, which is the Bateman equation. So doing the simple calculation, it becomes Na lambda b divided by Na lambda a equal to lambda b divided by lambda b minus lambda a into 1 minus e raised to whole minus lambda bt minus lambda at. Since the magnitude of 1 minus e raised to whole minus lambda bt minus lambda at is very small, we can neglect and we get the final equation of transient equilibrium, that is activity of B divided by activity of A equal to lambda b by lambda b minus lambda A. So this is the equation of transient equilibrium. Now let's look at the activity time graph of transient equilibrium. So, in transient equilibrium, the time to reach equilibrium is 5 to 10 half-lives of the daughter. When transient equilibrium is achieved, the daughter activity exceeds that of the parent. From the graph, here the dotted blue line represents the activity of daughter nuclei and the red line represents the activity of parent nuclei. It is clear that it is increasing from 0. The activity of daughter nuclei is increasing from 0 and after reaching a maximum, it is exceeding the activity of parent. And the daughter activity decreases according to the half-life of the parent. And after achieving maximum, it is coming towards the x-axis, that it shows that it is decreasing. So this is all for the activity time graph. Now next is the concentration half-life graph of transient equilibrium. In transient equilibrium, the concentration of parent nuclei significantly decreases in time. And the next point is the parent nucleate and the daughter nucleate may decay at essentially the same rate, but both concentration of nucleates decreases as the concentration of parent nuclei decreases. Here, the dark line represents the activity of daughter nuclei and the another line represents the activity of parent nuclei. It is clear that it is decaying at essentially the same rate, but it is decreasing according to their half-life. That is, it's the concentration of parent and daughter nuclei decreases. So this is all for the transient equilibrium. Now let's move on to the next topic, that is no equilibrium condition. In no equilibrium, half-life of parent is less than that of decay product. Here, decay constant of parent is greater than daughter, lambda 1 greater than lambda 2, which is exactly opposite condition of transient equilibrium. Let's see an example. Here we can see xenon with a mass of 138 is undergoing disintegration to produce cesium with a mass of 138, and the process continues and the final product is barium with the same mass. Here we can see the half-life of parent is 14.08 minutes and the half-life of daughter is 33.41 minutes, which is clear the half-life of daughter is greater than the half-life of parent. That is, xenon 138 is short-lived compared to its daughter product cesium 138. Now let's look on to the graph. So if the parent's half-life is shorter than that of the daughter, equilibrium cannot be achieved, which is the condition for no equilibrium. And here also in the graph, the dotted blue line represents the activity of daughter nuclei and the red line represents the activity of parent nuclei. The daughter activity increases from 0 and reaches a maximum and decreases at a rate primarily determined by its own half-life. We can see that it is increasing from 0 and then after reaching, it is approaching the x-axis, that it shows that the activity is decreasing. And there is no increase in the total activity with time. The activity will only decrease. That is, there is no equilibrium, there is no increase in the activity, that it shows only decrease in the activity. So that's all what I wanted to discuss with all of you. Thank you for listening to me. I hope all of you get the concept. So now I invite my friend Devika Mohan to deal with the further topics. Thank you.
Hello everyone. Now we are going to see the topics measure of radioactivity, its units and specific activity. We all know that some elements possess the radioactivity and we usually say a sample is highly radioactive or low radioactive like that. So we must be saying this based on something. So I wish to start by asking a question. What do we mean when we say a source is highly radioactive, or on what basis do we measure the radioactivity? So we need a parameter or a factor to define the radioactivity, and for this we have the activity. The activity, also known as the measure of radioactivity, is defined as the rate of decay or decay per unit time. We know that the process of radioactive decay is the disintegration of unstable nuclei to become a stable one. So this number of disintegrations that happen in a unit time is the activity of a radioactive sample, and it is usually denoted by the letter R. Here are few equations of activity. The first one is R equal to minus dN by dt, where dN is the number of decays that occur in dt type, and here the negative sign shows that the number of nuclei decreases over time. And other one is R equal to lambda n, where lambda is the decay constant. Here n can be expanded as n0 e raised to minus lambda t, where n0 is the number of nuclei at a time t equal to 0. That is we seen in the next equation, R equal to lambda n0 e raised to minus lambda t. And the next one is R equal to R0 e raised to minus lambda t, where R0 is the initial activity. And the next one is a relation involving T half, the half-life, and that is R equal to 0.693 n by T half. The activity can be also defined as a number of disintegrations per second, and its SI unit is becquerel, which is named after the discoverer of radioactivity. And these are some of the factors that depends and which are independent of the activity. The activity, as we have seen in the equation for R equal to 0.693 n by T half, it is directly proportional to the n, that is the number of nuclei, and is inversely proportional to the half-life. And these are the two factors that depends the activity, and the factors like type of decay, energy of decay products, and biological effects of radiations are independent of the activity. And the next one is a graph that showing the relation between activity and half-life, and as you can see the graph is an exponential decay function. So as the half-life increases, the activity is decreasing exponentially, and with the end of the first half-life the activity decreases to the half, and after two half-life the activity becomes 1 by 4. This continues until the sample reaches a stable state. The next one is the units of activity. There are many units for activity. The three main units are becquerel, curie and Rutherford. As we have already seen, the becquerel is a SI unit of activity, and one disintegration per second is a becquerel. The unit curie is actually the activity of 1 gram of radium, that is 3.7 into 10 raised to 10 becquerel or disintegrations per second, and the unit is given the name in the honor of Marie Curie's work with radium. And another unit is Rutherford, that is 10 raised to 6 disintegration per second. The next one is a problem related to the activity. The decay constant of copper is given, and we have to find the activity of 1 milligram of copper. The atomic weight is also given. So we have to find the n and the number of atoms. The activity is given as lambda n, lambda is given, and to find n we know that the 1 mole of copper contains Avogadro number of atoms. From this we can see the n, that is the number of atoms in 1 milligram of copper, as 9.9 0.45 into 10 raised to 15. So just by multiplying lambda and n, we get the activity as 1.43 into 10 raised to 11 disintegrations per second. So to convert this into the unit Curie, we have to divide this by 3.7 into 10 raised to 10. That is, we get as 3.86 Curie. And next one is specific activity. It is defined as the activity per quantity of a radionuclide, and it can also set as the activity per quantity of atoms. Its unit is becquerel per gram of Curie per gram. And as you see, the becquerel and Curie are the units of activity. And coming to the specific activities, it is becquerel per gram or Curie per gram. Okay, thank you. That's all from my topic.
Thank you, Devika. That was quite a lot of information. I'm going to discuss with you about the topic radiocarbon dating. On hearing a new thing, many questions arise in our mind, isn't it? We will proceed our discussion following these questions. So, the first question would be, what is this radiocarbon dating? Radiocarbon dating is a method for determining the age of an object containing organic material by using the properties of radiocarbon, a radioactive isotope of carbon. The foundation for this radiocarbon dating was laid by Martin Kamen and Samuel Rubin. In 1939, Martin Kamen and Samuel Rubin of the Radiation Laboratory at Berkeley began experiments to determine if any of the elements common in organic matter had isotopes with half-lives long enough to be of value in biomedical research. And they synthesized carbon 14 and soon discovered that the atom's half-life was far longer than that had been previously thought. But the carbon dating that we see today was developed by Willard Libby, and he was an American physical chemist. In 1945, Libby moved to the University of Chicago, where he began his work on radiocarbon dating, and he proposed that the carbon in living material might include carbon 14, that is the radioactive one, as well as the non-radioactive carbon. Libby and James Arnold proceeded to test the radiocarbon dating theory by analyzing samples with known ages, and for example, they took the samples from the tombs of two Egyptian kings, Soser and Sneferu, independently dated to 2625 BC plus or minus 75 years, and was dated by the radiocarbon measurement to an average of 2800 BC plus or minus 250 years. And these results were published in the Science in 1945. For his contributions to the development of radiocarbon dating, Libby was awarded Nobel Prize in Chemistry in 1960. And the Libby's curve of nonce compared the known age of historical artifacts with their age as determined by the radiocarbon dating, and the agreement between these two within a small margin of error demonstrated the accuracy of this technique. So far we have discussed what is radiocarbon dating and who invented it. Obviously, the next question would be, how is it done, isn't it? The basis of radiocarbon dating is that radiocarbon, that is radioactive isotope of carbon, that is carbon 14, is constantly being created in the atmosphere by the interaction of cosmic rays with atmospheric nitrogen. And the incoming cosmic rays create atoms of carbon 14 by colliding with nuclei in the upper atmosphere, liberating neutrons. And these neutrons, in turn, interact with nuclei of nitrogen in the air, replacing one of the 7 protons of nitrogen and it with an extra neutron, and the resulting atom, now containing 6 protons and 8 neutrons, is one of the carbon 14. So we will move on to the next slide. It is, how is this process? That is, how does this carbon 14 in the atmosphere reach living matter? It is based on the fact that the carbon 14 is constantly being created in the atmosphere. We have known that. And this carbon 14 combines with atmospheric oxygen to form radioactive carbon dioxide. And this is incorporated into plants through photosynthesis, and animals acquire this carbon 14 by eating the plants. When this animal or plant dies, it stops exchanging carbon with its environment, and thereafter, the amount of carbon 14 it contains begins to decrease as the carbon 14 undergoes radioactive decay. Measuring the amount of carbon 14 in a sample from a dead plant or animal, such as a piece of wood or a fragment of bone, provides informations that can be used to calculate when the animal or plant died. That is, older the sample is, the lesser amount of carbon 14 to be detected in the sample. In the following image, it shows the half-life and the further decay details of carbon 14. 5730 years is the half-life of carbon 14, and further on. We are moving on to the next slide. In this, we are going to discuss about different types of radiocarbon dating. The first one is gas proportional dating. It is a conventional radiometric dating technique that counts the beta particles emitted by a given sample. And these beta particles are products of radiocarbon decay in this method. And the carbon sample is first converted to carbon dioxide. That is, all the carbon present in the sample is converted to carbon dioxide before measurement, and the gas proportional counting takes place. The next one is liquid scintillation count. It was a method which was popular in the 1960s. In this method, the sample is grounded into small part pieces and which is treated with a weak acid, and then it is freeze dried. This sample undergoes various chemical reactions to convert all the carbon atoms in it to benzene. To this mixture, a scintillator is added, and this mixture is passed through a liquid scintillator spectrometer which counts the number of decays occurring per minute. And after the computer analysis, we obtained the age of the sample. And the third one is accelerator mass spectrometry, which is the most efficient and accepted method. In this method, the carbon 14 content is directly measured relative to the carbon 12 and carbon 13 present in the sample. And the method does not count beta particles, but the number of all the carbon atoms present in the sample is counted. And now we will see about the uses of this carbon dating. As per the definition, it is used for determining the age of earth materials like rocks and fossils. It also helps in archaeological studies and excavations, and also to disprove and prove the theories of archaeology and human sciences, also in forensic proofs. There are many crimes occurring around us, isn't it? So, carbon dating plays a major role in the proof of these crimes. And carbon dating is also known by the names radiometric dating, thermoluminescence, and half-life dating. So far, we have seen the properties and definitions of radiocarbon dating. We have seen that it's used for determining the age of a object. So there must be some equations, isn't it? Now I invite my friend Sneha for further details in this subject. Thank you.
Thank you, Binta, for your wonderful class. It was an excellent one. Now, friends, we are going to see the rest of the portion, radiocarbon dating. So we have learned about how it works, its properties, and so on. Now we will begin our section by discussing with the formula for finding the age of a sample with organic material embedded in it. So the sample can be fossil or any other material with a organic material embedded in it. So the formula is
T is equal to natural logarithm of n divided by n naught the whole divided by 0.693 into T half, and here T half is the half-life of isotope carbon 14 and T is the age of the fossil. Next, we will move on to an example based on the formula. Here we need to find the age of a fossil that has 35% of carbon as compared to living sample. So, here we are going to study or the age or determine the age of a fossil that has 35% of carbon as compared to the living sample. So according to the question, the data is provided at n is equal to 35%, T half is equal to 5730. On substituting these values in the formula that we had learned, we will get the final answer T is equal to 8680. So the fossil is 8680 years old. This means that the living organism died 8680 years ago. Next, as Binta had discussed in her topic importance or uses of radiocarbon dating, we have discussed a point that the radiocarbon dating has a great importance in the field of archaeology. It is a tool for dating the past 50,000 years. Here we are going to learn about the two types of dating used in the archaeological field, and we will discuss them in the form of a comparison. The first one is relative dating and the next one is absolute dating. On moving on to the relative dating, the dating is based on a comparison of futures. It might be external, internal futures. Whereas absolute dating, it is a numerical type of dating which is based on radioactive decay that we had learned. In the case of relative dating, it is just a comparison. It's not an exact age. It will give just an estimate of the age of the sample. However, in the absolute dating, as the name suggests, it gives an exact age of the sample that we are considering. So, this is the difference between the two types of dating used in archaeology. Next, we are going to see the assumptions on which the radiocarbon dating is used. The first one is that the production rate of carbon 14 must be constant. The carbon 14 must be produced in the same in the past as now. How the second one is that the constant carbon 14 concentration in atmosphere, that is, atmosphere must also have the same carbon 14 concentration in the past as now. And the third one is that the biosphere and atmosphere has same carbon concentration. The biosphere has always the same overall carbon 14 concentration as the atmosphere. This is because there is a rapid transfer of carbon 14 atoms from the atmosphere to biosphere. Hence, they should maintain a constant carbon concentration both in atmosphere and in biosphere. So these are the three assumptions on which radiocarbon dating is used. Now we are moving on to the limitations or drawbacks of carbon dating. First one is that the carbon dating, radiocarbon dating is limited to about 50,000 years. The older the object or matter, the less carbon 14 will be there to measure. This point is already discussed by Binta in her slide. The next one is that the radiocarbon dating is susceptible of contamination. There is a possibility of contamination. Contamination in this sense means that the sample may be contaminated by other carbon containing materials like the soil that surrounds the material, for instance the bones or labels that we are considering. So there is a possibility of susceptible of contamination. The third one is that the radiocarbon dating is not extremely accurate. This is because we know that we are doing radiocarbon dating chemically. So we cannot figure out the exact time of death or decay. For example, if we found that a particular fossil is 60,000 years, then we will be about 3 to 10 years late. Similarly, if it was on the scale of 6 hours ago, we could be 3 to 5 minutes late. So the radiocarbon dating is not extremely accurate. Even though the radiocarbon dating has these all disadvantages, it is a tool for measuring or merging us into the past without going there. Radiocarbon dating has revolutionized our understanding of past. Finally, The carbon 14 and radiocarbon dating needs careful attention because if one step is missed or performed as incorrect, you have to start the entire program once more. So these are the limitations. Next, we are moving. Um, have you ever thought that why carbon is the basic factor of radiocarbon dating? Have you ever thought? Yes, carbon is the basic factor. This is because due to the 4 points given in this slide. First one is that carbon 14 is a radioactive isotope of carbon. That is, the carbon 14 has an unstable nuclei. It decays at a constant rate. Hence, carbon 14 is the basic. Next one is that carbon 14 has a half-life of 5730 years. And carbon 14 decays into nitrogen 14. Then the carbon is present in all living things. Hence, it is a measure for dating the materials because the carbon is present in all living things irrespective of humans or plants. Carbon is everywhere. So all living things contain carbon. Hence, the carbon 14 is the basic factor of dating. Next, we are moving on to the topic rock dating. As we have discussed in the topic limitations, radiocarbon dating is limited to 50,000 years. But we know that the Earth history goes back 4.5 and so billion years. It is necessary to date or to find the age of material that has existed since the evolution of Earth. So, the geologists use radionuclides of much longer half-lives to date rocks. That is, in rock dating, the geologists use radionuclides of longer half-lives. In this case, we assume that all the stable daughter nuclides found in a particular rock sample come from the parent nuclei. That is, all stable daughter nucleides from a particular rock sample that we are considering come from the parent one. This dating is often referred to as geological dating. Here, the parent nuclei is one whose nucleus undergoes a radioactive disintegration, and the product nucleus formed is the daughter nuclei. So, this method is referred to as geological dating. There are many different types of methods used in geological dating. And before moving on to, we will discuss with the equation used in geological dating, that is T is equal to 1 by lambda natural logarithm of n0 divided by n. Here n is the number of atoms of parent nucleide and n0 is the number of both parent and daughter nucleides. The 2 points that we need to remember with the equation is that here T, the age depends on the nature of the rock that we are considering. And the greater the proportion of the daughter nuclei, the older will be the specimen. So hope you understand well. So we already say that there are different methods used in geological dating. Here we are moving on to the two types on the basis of the comparison, that is the potassium argon dating and uranium lead dating. The potassium argon dating is used to date rocks of 60,000 years older and older. The time period of dates in which the potassium argon dating is used is 60,000 years older and so on. However, in uranium lead dating, it is used to date rocks whose age is from 1 million years to 4.5 billion years old. In potassium argon dating, as the name suggests, it is based on the radioactive decay of potassium into argon, whereas in uranium lead dating, it is based on the decay of uranium to lead. So we are moving on to the end of the presentation and we will end by discussing two questions. Can humans be carbon dated? Have you ever thought that humans be carbon dated? So the answer is that we are very eager to watch movies based on crime, detective and so on. In most such movies, we can see a special character named forensic scientist. So this forensic scientists just use it to determine the age, the year of the death, etc. in cases involving unidentified human remains by the method that we are discussing, that is the radiocarbon dating. So, the measuring carbon 14 levels in human tissue will help the forensic scientists to determine the age, the year of death in cases involving unidentified human remains. So, the next question is that why carbon dating is not useful for dating diagnosis? Is carbon dating is used for dating diagnosis? No, the carbon dating is not a method for dating dinosaurs because we know that the dinosaurs lived on Earth 65 million years ago. As we have discussed that radiocarbon dating is limited to 50,000 years. This means that we cannot figure out the age of dinosaurs or fossils or any other ancient mammals or reptiles that lived before this particular time period. In order to find their age, the scientists will use the isotope of longer half-lives like uranium 238, potassium 14, etc. So the radiocarbon dating is not a method to date dinosaurs. So hope you understand well the questions. So here we are giving some references, that is these are some of the links from which we gathered the information regarding the topic. For more convenience, you may please visit these sites and grasp additional knowledge. So I hope that the entire presentation is clear to you. If there is any question regarding radioactive equilibrium, you may please uh, give me the suggestions. Um, this is the end. We have learned about radioactive equilibrium, measurement, radiocarbon dating, and so on. So I believe that you all understand well the concepts behind these topics. So this is the end of the presentation. Thank you so much for having an opportunity to present before you. Thank you for listening.